Pluto is a far-off and secretive, more unassuming planet that was once a part of our planetary system. However, recent alarming statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a stunning discovery. They propose that this frigid world is on a potential crash course with Neptune. But how could this happen? And what might be the consequences of such a massive event? Are we witnessing an intriguing cosmic peculiarity? Or is there more to this impending celestial mishap? Join us as we explore the potential consequences of a Pluto-Neptune collision. Pluto, a former planet downgraded to a dwarf planet partly because of its unusual orbit, remains a subject of fascination and study in the cosmic community. According to recent estimates by leading scientists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a potentially catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It takes an astounding 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, straying significantly from the almost circular orbits of the major planets. What makes Pluto's orbit even more unique is its inclination of 17 degrees to the ecliptic plane. This means Pluto's path is much more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to understand its peculiar path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amid these complexities is evidence of the intricacies of space mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and interact with one another through gravity. It's like predicting where they will go based on where they start and how they pull on each other. In Pluto's case, this issue illustrates how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. Terms such as apsidal libration and nodal libration, along with the VZK oscillation, are crucial parts of this puzzle. According to astrophysicists, what keeps all planets in their orbits is apsidal libration. Regarding Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from merging. Nodal libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of safety from possible collisions. Another significant factor in this situation is the VZK oscillation, named after three scientists, VZK. Who studied how objects move in space. It involves how three celestial objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This gravitational tug influences how they move. In Pluto's case, the VZK oscillation helps us understand why its orbit around the Sun is so unusual. Despite Pluto's orbit appearing erratic, this oscillation ensures it moves smoothly over long periods. The VZK oscillation shows that, although space may seem chaotic and unpredictable, certain patterns and forces maintain order. All these factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. This three-body problem is critical to understanding how these orbits change based on the way celestial objects interact with one another. Studying this helps us learn more about Pluto and our solar system, as well as distant planets and their stars. Numerical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is actually chaotic, with minor deviations in initial conditions leading to significant changes over thousands of years. However, these surprising properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, keeping disruptions in check. Later computational models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where, for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only player in this. Jupiter's gravity also plays a crucial role in stabilizing Pluto's orbit, as does Saturn's. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for an exceptionally long time, even millions of years. It's as though Neptune, Jupiter, and Saturn are all working together to ensure Pluto continues to move safely through space without encountering trouble. These peculiarities are essential for maintaining order and stability in space. Without these factors, the solar system, as we know, would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, particularly with discussions about it possibly colliding with Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of the solar system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of harmony through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of this oddity. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is vividly illustrated by Pluto's case. Orbital chaos, in the context of Pluto's trajectory, underscores the delicate balance maintained by gravitational forces over immense timescales. While Pluto's orbit appears unpredictable when observed over shorter durations, the broader picture reveals an intricate, self-regulating system. This apparent chaos is mitigated by the gravitational interactions between Pluto, Neptune, and other massive bodies in the solar system, ensuring long-term stability. The role of resonances in stability. A key factor in maintaining this balance is orbital resonance. As mentioned earlier, for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This 2:3 resonance prevents close encounters between the 2 bodies, ensuring they never collide despite the overlapping nature of their paths. Resonances like these are not unique to Pluto and Neptune. They are common in the solar system and play a vital role in maintaining the orderly motion of celestial bodies. Could the stability be disrupted? Despite the mechanisms that stabilize Pluto's orbit, small perturbations from external forces, such as the gravitational influence of passing stars or interstellar objects, could, theoretically, disrupt this equilibrium. However, such disruptions are incredibly rare due to the vast distances between solar systems and the protective gravitational pull of the Sun, which dominates the motions of objects within the solar system. The broader implications for Earth and the solar system. The hypothetical collision between Pluto and Neptune, while highly unlikely, raises important questions about the interconnected nature of the solar system. A major disruption to Pluto's orbit could set off a cascade of changes, affecting the orbits of other celestial bodies, including smaller asteroids and comets. This, in turn, could increase the likelihood of collisions elsewhere, potentially impacting Earth. However, current models and simulations suggest that the solar system is remarkably stable over billions of years. This stability is a testament to the finely tuned interplay of gravitational forces that have shaped the motions of planets, moons, and other bodies since the solar system's formation. The future of Pluto. As technology and observational techniques improve, scientists continue to study Pluto's unique orbit to gain deeper insights into its long-term behavior. Observations from missions like New Horizons, which provided unprecedented detail about Pluto's surface and composition, also contribute to our understanding of its broader orbital dynamics. Pluto's story serves as a reminder of the intricate dance of forces that govern the cosmos. Its orbit, while seemingly chaotic and unpredictable, ultimately follows a path that has been forged by billions of years of gravitational interactions. The study of Pluto and its interactions with other celestial bodies not only enhances our understanding of the solar system, but also inspires the complex and beautiful mechanisms that govern the universe. In the end, while the idea of a catastrophic collision between Pluto and Neptune makes for an intriguing thought experiment, the reality is far less dramatic. The forces that have kept Pluto in check for billions of years are likely to continue doing so, ensuring the ongoing stability of the solar system and the fascinating mystery of this distant, icy world. Pluto. This implies that even slight changes in the Bantam planet's situation or speed can drastically alter its long-term orbit. Utilizing computational models has been immensely helpful for researchers in understanding how Pluto moves in space. These simulations use complex science to model how Pluto and other space objects, like Neptune, interact and pull on each other. By tweaking small details in these simulations, astronomers can observe how even minor changes can significantly impact where Pluto ends up. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Even though it has mechanisms like axial inclination and orbital resonance to keep it stable, its orbit can still be unpredictable and chaotic. If you start with only a small difference in Pluto's position or velocity, its orbit could look completely different after a number of years. However, even with this chaos, Pluto's orbit remains stable over incredibly long periods, spanning billions of years. This means that Pluto's journey around the Sun has a kind of order, despite appearing turbulent at first. Predicting celestial events, especially when involving irregular orbits like Pluto's, is a monumental challenge. The inherent instability of such systems means that long-term predictions are often fraught with uncertainties. While mathematical models provide valuable tools for understanding and forecasting the future paths of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Additionally, the chaotic nature of planetary orbits like Pluto's reminds us of the dynamic and ever-changing nature of the universe. Despite significant advances in understanding space, Pluto's case serves as a humbling reminder of how limited our knowledge of the cosmos remains. Understanding the gravitational effects of the giant planets on Pluto's orbit provides crucial insights into the broader dynamics of the solar system. It demonstrates how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite all these complex forces working to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist and influential figure in popularizing cosmology, offers an intriguing perspective on the mysteries of our solar system, particularly the curious case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the uncharted realms of space. Tyson views Pluto's reclassification not as a demotion, but as a significant adjustment to our expanding understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, like Pluto's, as a testament to how much remains to be discovered in space. The fascination with these questions keeps the exploration of space endlessly intriguing. However, despite Tyson's optimism, his thoughts on Pluto's possible collision with Neptune paint a much more uncertain future. He emphasizes that Pluto's and Neptune's orbits will continue to evolve, driven by forces that are sometimes unpredictable. Interestingly, Tyson also mentions that these uncertainties could potentially bring Pluto closer to Neptune's orbit over the next few million years. Nonetheless, he remains cautiously optimistic about the likelihood of such a collision. Tyson suggests that while the odds of such an event occurring in the short term are low, the unpredictable nature of planetary orbits means we cannot entirely rule out the possibility of such an impact in the distant future. In addition to Tyson, Michio Kaku, a renowned theoretical physicist, also weighs in on the implications of a potential Pluto-Neptune collision. Kaku's analysis combines cutting-edge physics with a deep understanding of cosmic evolution. He believes that such a collision, if it were to occur, could have profound implications, not just for Pluto and Neptune, but for our understanding of the universe as a whole. According to Kaku, a Pluto-Neptune collision could trigger a cascade of other events, perhaps even altering the nature of the solar system as we know it. However, he also acknowledges that the chances of such a dramatic event occurring in the near future are exceedingly unlikely. He points out that while Pluto's and Neptune's orbits are in close proximity, the vastness of space and the complexities of their orbital dynamics make a collision improbable in the short term. Nevertheless, the possibility remains an intriguing topic for further study and speculation within the scientific community. In conclusion, the potential for Pluto to collide with Neptune remains a subject of active debate among astrophysicists. While the dynamics of their orbits currently prevent a collision in the short term, the complexities of celestial mechanics mean we cannot dismiss the possibility of such an event occurring in the distant future. The ever-changing nature of planetary orbits reminds us of the dynamic and unpredictable nature of our universe. Whether or not such an event happens, it serves as a fascinating example of how much we still have to learn about the future of the solar system. Expanding on the discussion, the study of celestial mechanics, particularly cases as complex as Pluto and Neptune's interactions, offers significant opportunities for advancing our understanding of the solar system. By observing and modeling their orbits, scientists can derive insights into broader cosmic principles, such as gravitational resonance, orbital stability, and chaos theory in space dynamics. One of the critical aspects of Pluto's orbit is its 2:3 resonance with Neptune, meaning Pluto completes 2 orbits around the Sun for every 3 orbits Neptune completes. This resonance ensures that despite their overlapping orbital paths, Pluto and Neptune never collide. The gravitational interaction between these two bodies maintains this synchronization, acting like an invisible cosmic safeguard. However, this stability, while enduring over billions of years, may not be absolute. Even subtle changes, such as perturbations caused by other planetary bodies or interstellar influences, could theoretically disrupt this resonance over immensely long timescales. Such disruptions could shift Pluto's orbit into a path that brings it closer to Neptune, increasing the likelihood of an encounter. This hypothetical scenario underscores the importance of continuously refining our computational models to account for every variable, no matter how minute. Astrophysicists also emphasize the role of external factors, such as rogue asteroids or the influence of passing stars, which could introduce additional instability into the solar system. These rare events could potentially alter the gravitational equilibrium between Pluto and Neptune, leading to outcomes that are currently unpredictable. Beyond the technicalities of orbital mechanics, the public fascination with Pluto's status and its potential interactions with Neptune reflects a broader curiosity about the dynamic and evolving nature of our solar system. The reclassification of Pluto as a dwarf planet may have sparked debate, but it also reignited interest in understanding the complexities of celestial bodies beyond the 8 primary planets. Pluto's peculiarities, its highly elliptical orbit, its inclination relative to the ecliptic plane, and its composition, make it a unique subject of study. Alongside Neptune, it serves as a reminder that the solar system is far more diverse and intricate than previously imagined. Studying such systems not only enhances our understanding of their past and future, but also sheds light on the processes shaping other planetary systems in the galaxy. Looking to the future, continued advancements in technology, such as more powerful telescopes, interplanetary probes, and AI-driven simulations, promise to refine our knowledge of Pluto and Neptune's relationship further. Missions like the New Horizons spacecraft, which provided groundbreaking insights into Pluto's surface and atmosphere, highlight the value of direct exploration. Future missions could focus on studying the gravitational interplay between Pluto and Neptune, providing data to validate or challenge existing theories. Ultimately, the story of Pluto and Neptune is not just one of potential collisions or orbital chaos, but a testament to the richness and complexity of the cosmos. It reminds us that the universe operates on scales of time, distance, and complexity that challenge human comprehension. Each discovery, whether about Pluto, Neptune, or any other celestial body, is a step toward unraveling the mysteries of the universe and our place within it.